Sorry, everybody. We didn't have the audio going in, so we started getting into things without you hearing us. So this is the first Student Mentor Showcase. I am here with Mentor Ben, and he's going to show us a project he worked on. So even though you described it just before, Ben, sorry about that. Could you do us all a favor and start from the beginning again?
Absolutely. So, hello everyone. I'm Mentor Ben, and what I'm going to show you today is a fun little Python project that I was working on a few weeks back. It basically came from I was kind of exploring digital audio a little bit, how computers store music and sound and all sorts of, all the sorts of things that you listen to in a game or from a YouTube video or in any way, shape, or form. And um, Python is pretty good for working with stuff like this, getting things done quickly and easily. So I opened up a Python file and got to work. And really, Python has a library that makes this a lot easier, that lets you work with Wav files. I have this at the top of my code here. You can see that. So what is a Wav file? First of all, I should explain that. A WAV file is one of the most common ways of storing audio. There's many different audio formats. You might be familiar with MP3s and MP4s, OGG files or OGG files, if you want to pronounce it like that. There's WAV files as well, and WAV files are just one of many different ways of storing audio data in a way that a computer can understand and use to replicate music and sound and all sorts of other things like that. So Python lets you, when you combine Python basic functionalities in Python with this concept, you can actually get pretty far pretty quickly. So I'm going to explain pretty quickly with this visual, just what this program is actually leveraging and how it works. What I have here is a representation of how digital audio is stored. So you may be familiar with the concept of like sound waves that come from sine waves, if you've ever heard of that term. And basically what really matters here is that sound can be represented by a collection of waves. And with the right set of waves, you can replicate a piece of music, an instrument, a sound effect, anything like that. So with enough, and these waves are, by the way, actually, they exist physically. They're not just concepts. By definition, what sound is rapid compression and rarefaction of air. And if you want to get really like technical with it, you can look at the way that sound waves form and whatnot. But what all we really need to worry about, rather than the intense physics behind it, is the way that computers can kind of represent sound. If sound is a complicated wave, and it's not really repetitive, it's kind of, it almost looks random, although I will assure you it's not actually random. But a computer can't store every single point on this graph at once. So what instead a computer will do is known as sampling. And sampling is really just a way of saying, I'm going to take just enough points so I can kind of figure out what the sound is going to look like. So if I take, each of these blue points, I can kind of get a good idea of where this wave is going, right? If I connected the dots, it's not perfectly lined up with the red line that the graph is represented by, but it's pretty close, right? You can imagine if I move my mouse along here, you kind of see that what these blue dots represent. And so WAV files actually just store each of these blue dots one after the other. So this one, it'll store a -4, for example, for this blue dot. It'll store a 0, it'll store then a 4, then a 7, then a 6, one after the other, just nothing in between. And so with just this minimal data, you can represent complicated sounds. And it's in practice a little different from this, right? You have to shift the range up so that it works with the byte, and you have to set the range from 0 to 256. I'll show you that in a second. But this is kind of the framework for understanding what this program is doing. So now I will open the actual program up on the left side here, and I'll show you the output folder on the right. So here is the project. And first, I'm just going to run through it. I'm going to run the program and show you what it does. So I'm going to click run, and I'll do run module just to run this program. So immediately the program asks me to enter a note. And so as a person who made this, I know the format that has to be entered. It's basically asking to enter a musical note. So I'm going to enter the note, let's say, let's go with F4. F4 is a kind of this isn't really, I'm not going to get too deep into it, but it's a way of representing a note, the letter F. If you have familiar with if you're familiar with pianos, for example, you may be familiar with a scale and what if you've played a musical instrument at all. But F is a musical note, and 4 just represents how high or low it is, which octave it's in. So F4 basically is a specific musical note. And I'm just going to hit enter, and I'm going to add A4, so another note, A, and I'll say C. I'm actually going to put C5, the next octave up. I'll explain this in a second. So what this is going to do now, right? Because this is a chord generator. So this program is going to create a wave file that has a chord stored inside it based on these notes, the notes that I input. So the wave file that this program is going to output and create when I finish inputting all my notes will have the notes F, A, and C. And that's going to sound like dun, 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 something like that. And it'll create a chord, which I will play for you. I'm going to hit enter, and the program is done. So what happened? Nothing changed. Well, because this was a program that I created just to kind of play around with the concept, I wasn't really too organized with this. So I just created the file, and now I'm going to find it and show it to you. I have a lot of files here. It should be somewhere in here. All files. And it should be called chord.wave. Here it is. And you can see it just created it now, 7/15/2021, 5:52, the time that I am saying this line right now. I'm going to take this and drag it into this folder where I can play it back from, just because this is the Python folder. So it's going to try to open the audio file using pure Python, and it can't do it because it's not a Python file, it's a WAV file. So we don't want that. Instead, I'm in this folder that's pretty much right off of, I believe it is my desktop. And so Windows kind of knows what program to open it with. It'll open it with the program that plays WAV files back. So I'm going to click on this to open it. And what you'll hear is a chord. And it loops over and over again. And I can repeat this again just to show you that I am actually creating the chord based on these notes. I'll run the program one more time, run module, and I'll make, let's go with some other notes.
Now I'm going to ask you a question that some other people may be wondering.
Yep.
I'm guessing you play an instrument, Ben?
I do, but for this program, it wasn't the only musical knowledge you need is a way of representing these notes. And realistically, you actually you can get around that if you find a way to build the. It's hard to explain, so I'm not going to go into detail here. But basically, each note has mathematical connections to other notes, so there are ways to get around it. But yeah, it did help with the notation.
Well, I think it also just helps in playing some nice sounding chords. You're not
Oh yeah,
playing
that's
tritones or anything aggressive sounding like that.
yeah, definitely. I mean, I could, if you want me to play a really horrible sounding chord, I could do that, but I'm gonna refrain from doing that, I guess, for now. So I have a second chord.wave. I'll just overwrite it, and just to show you that this does in fact work, this is a different chord now. Still high pitched, but different notes. It's hard for me to play them back and forth, but trust me when I tell you that was a very different chord. So.
And so, I do have a question. Is there a limit to the number of notes you can place in a chord with your program?
I haven't reached it if there is, because, and I'll explain why. Actually, right now it's going to get into the way the program works. So let me do that, and then I will. So yeah, so I've showed you what this program does, and I'm just going to go into the details now, explain it a little bit more. So at the top here, we're just importing the libraries we're using. The Wav library lets me work with WAV files very easily. It's a standard library. Python 3 has it built in. There's also the math library. I'll show you why I use that when I get to generating the sound. And I also have this funny looking line of code here, which is something I was using to debug the project. This is just to graph the wave, which I can show you at the end, but it's not super important to us right now. So there's a lot of ways that I could have done this next part, but each note that you heard, each note that I input, can be represented by a different frequency. And the word frequency is a really fancy way of saying that when I look at this wave, and let me pull it up again, right? this is not a repeating wave, right? We go all the way up, then we go down a bit, then up a bit, then all the way down. And and it may repeat, if we let it play out more, it'll eventually start cycling around. Let's imagine I had a wave that just went up, down, up, down, up, down, up, down, over and over and over again. How fast that wave repeatedly goes up and down, or how many cycles the wave actually completes within a second, is its frequency. So a frequency is just how fast the wave goes back and forth. And when it comes to sound, the frequency of a sound is just how high or low the sound is. And that's just because of the way that the human brain actually, it sees sound. I can't really explain that to you. You'll have to take my word for it. So, but what you can do is I copy and pasted from some online source the frequencies of each note, kind of reformatted it into a Python dictionary so that each note is mapped to a frequency, or how many times per second a wave should repeat itself. So that means, for example, this super low note, C0, means that within 1 second, the sound wave that represents this note, that plays this note, will repeat 16.35 times, and that means it won't finish a 17th cycle. So it'll get 16 cycles and then a third of another one, almost, or about. And each note has its own frequency as you get higher and higher and higher, because the frequency will also get higher and higher and higher. Some notes you'll see match up, and this is more musical information, but we're going to discard this for now. But basically, understand that each note has its own frequency. And I've also created a list of all the notes that are valid. So A sharp, B sharp, musical notes that the user might input that are, you'll see in actual music. And so here's really where the magic, I say magic in quotes, but here's where it comes in. So I showed you before that an audio file, right, like here, we can represent it. It's represented by waves, but we also don't need every single point on this wave to reconstruct the original audio, right? I can just take a point here, a point here, a point here, and eventually, if I take enough points, I'll have a pretty good idea of what the sound is actually supposed to sound like. So what I have here, if I go back to the program, is this function called sine wave. And it's a little misleading, not super descriptive, but a sine wave is a math concept that pretty much just, it's going to generate a wave normally. A normal sine wave goes back and forth over and over and over again, up and down, forever. So as you input a value x, you go farther and farther along, right? If I have this x, imagine this is like an xy grid. If I have some complicated sine wave, if I set x equal to, 2, maybe that'll be the second point here. X equals 2, well, what's the value of my sine wave function? You can look at the y value on the left, it's 0. And if I input x equals 3, you can go up here, y equals 4 when x equals 3. But basically, every input value of x will have some special y value that when you go kind of in a row, the one x value after another, you'll get this kind of wave out of the y values. And so the cool thing about audio is that when you want to merge multiple notes together, you can just take the two waves that represent those notes, right? So one wave, the example I used before had F4, and over here, F4 should be kind of to the right here. F4 had a frequency of 349.23, and then A4 was 440 on the dot. That's by definition. So if I would like to create a chord with both of these notes, I can just take the value of the wave that represents F4 and also take the wave that represents A4 and just add them together. And that's almost pretty much it. If I take a wave and add another wave to it, I will effectively merge those two waves. And what I'm really saying is, no matter what value of x I input, it turns out that you can just take whatever the value of x would be when you input it into the function that represented the F4, and then also put it into the function that represented A4, and just add the two results together, and that's pretty much it. Then you can do the same thing for the next note, C5 in that case. Add it to the entire result.
And this is largely what happens in real life too, physically. These waves, they go through constructive and destructive interference where the combination of that, the way the human ear picks it up and our brain interprets it, gives us these chords and sounds that we're so used to hearing. I did just want to point out a couple of things. You're creating sine waves here, and people may not know what that is. They may know what it is in math class, but a sine wave is going to sound like a really nice, clean tone. But there's a couple of other kind of waves, sawtooth waves, triangle waves, square waves, and those are going to sound really aggressive, like an alarm going off or something like that. So that's why you see the sine wave coming in here. That is actually how a nice clean tone is created. Otherwise you'd be using one of those other things. They have their purpose, but if you're trying to just create a regular chord, sine wave's usually the way to go. We don't have too much time here, Ben, but I did want to ask, do you have any plans going forward for where you'd like to see this project progress into, or anything that you'd like to do with it?
I'd say that the chord generator project was kind of a result of, exploring the way wave files worked, but I have considered kind of branching off into other directions as well. This was kind of a way, you'll see this, the sine wave function especially was kind of me working out how wave files work. And if I scroll down, you see the way, like, this is where I actually create the wave file and add all the notes to it. Write frames as a function that writes different frames to the wave file. A frame just representing each of these points. But I think this project was kind of a good way to get used to the way sound works. It's a very interesting topic. It's not intuitive at first. That sound is really just a bunch of waves that you can just add together to create lots and lots of complicated chords and music, and even whole instruments. Like the difference between a clarinet and a piano might just rely on which combinations of notes or which combinations of waves the instrument produces. So it's kind of cool. And in terms of code, I have worked on some other digital audio type of projects, and I'd like to explore the topic more in the future because it's very interesting, and to see where it can go with all the math and all the programming behind it.